Hello there, and welcome to Midnight Science. I'm so glad you found your way here, because tonight we're wandering into the quiet realm of trees, those patient giants that have witnessed centuries unfold, that clean the air we breathe, that shelter countless lives beneath their branches. Maybe you've had a restless day, or perhaps you're simply drawn to the peace that forests bring. Whatever your reason, this space is yours now. Let your breathing slow. Let your mind settle like fallen leaves on a forest floor. We're going to explore the gentle world of trees, how they talk to one another through underground networks, how they've survived ice ages and droughts, how a single tree can be home to thousands of creatures. Some discoveries will fascinate you. Others will simply wash over you like rain on leaves, soft and steady. If these quiet moments help you find rest, please take a moment to like and subscribe. It helps this corner of calm reach others who need it too. Also, I'd love to know where you're tuning in from and what time it is there. It's always wonderful to see how these videos bring people together from all around the world. Now, settle in, let the day's noise fade, and let's walk together beneath the canopy, where time moves differently and peace grows deep. Trees were here before dinosaurs. When you stand before an old tree, you're looking at something connected to deep time. The first trees appeared on Earth around 385 million years ago, long before the first dinosaurs walked the land. These ancient forests looked nothing like the ones we know today. Early trees like Archaeopteris had frond-like leaves and grew to heights of nearly 100 feet, creating Earth's first real woodlands. These primitive forests changed everything. They pulled carbon dioxide from the atmosphere, released oxygen, and cooled the planet. Their roots broke down rock into soil. When they died and fell, they created the coal deposits we mine today. They set the stage for almost all terrestrial life that followed. Dinosaurs would eventually walk beneath trees, but the trees were here first, waiting patiently in the silence of an empty world. A single tree can be an entire forest. In the dry mountains of Utah, there grows what appears to be a forest of quaking aspens, golden leaves trembling in the slightest breeze. But beneath the surface lies a secret. All those trees, every single trunk you see, are one organism, one tree. This massive grove is called Pando, which means I spread in Latin. It's a clonal colony connected by a single root system that spans over 100 acres. The individual stems you see are genetically identical shoots rising from those ancient roots. Scientists estimate Pando weighs around 6,000 tons and may be up to 80,000 years old, making it one of the oldest and heaviest organisms on Earth. Individual trunks live and die, but the organism persists. Pando has weathered ice ages, droughts, and the passage of millennia. It's a forest that is also a single being, breathing slowly, spreading steadily, and holding memory in its roots. Trees talk to each other underground. Walk through a forest, and you might think you're surrounded by individuals, separate trees living separate lives. But beneath your feet, something remarkable is happening. The trees are talking. Through a vast underground network of fungal threads called mycorrhizae, trees exchange nutrients, water, and chemical signals. These thread-like fungi connect to tree roots, forming a symbiotic partnership sometimes called the wood wide web. A mother tree, older and more established, can recognize her own offspring and send them sugars through these networks, If one tree is attacked by insects, it can send warning signals to its neighbors, allowing them to boost their chemical defenses before the pests arrive. This isn't metaphor. It's measurable, documented science. Trees share resources, support the weak, and warn of danger. Douglas firs connect with birches. Oaks link with maples. The forest isn't a collection of individuals competing for light. It's a community, quiet and cooperative, speaking in chemistry and need. Some trees can clone themselves for millennia. Reproduction usually involves seeds, flowers, and the mingling of genes. But some trees have found another way. They simply make copies of themselves, perfect genetic clones that rise from spreading roots. Aspens do this naturally, so do some poplars and willows. A single tree sends out underground runners, and from these shoots emerge what look like new trees. They share the same DNA, the same resistance to disease, the same response to seasons. In Sweden, there's a Norway spruce whose root system has been carbon dated to nearly 10,000 years old. The visible trunk is much younger, but the organism itself has been alive since the end of the last ice age. These clonal trees don't rely on chance or pollination. They endure through patience and persistence, spreading slowly across hillsides and valleys, one root, one shoot, one quiet century at a time. The tallest trees touch the clouds in the coastal forests of Northern California, where fog rolls in from the Pacific and the air stays perpetually moist, grow the tallest living things on Earth. Coast redwoods, Sequoia sempervirens, can reach heights of over 380 feet. That's taller than the Statue of Liberty, taller than most city buildings. The tallest known redwood, named Hyperion, stands at 380.3 feet. It was discovered in 2006, hidden deep in Redwood National Park. Climbing it is forbidden now, to protect both the tree and the delicate ecosystems that thrive in its upper branches. Yes, ecosystems. High in the canopy of these giants, entire communities exist: mosses, ferns, salamanders, and insects that never touch the ground. These trees can live for over 2,000 years. They've stood through empires, wars, and the rise and fall of civilizations. And still, they grow, reaching toward light with a patience we can barely comprehend. Trees invented wood, and it nearly froze the planet. There was a time, about 300 million years ago, when nothing on Earth could decompose wood. Trees had only recently evolved lignin, the complex molecule that makes wood hard and strong. But no organism had yet developed the enzymes to break it down. So when trees died, they just fell and stayed. They piled up in enormous quantities, layer upon layer, in swampy lowlands that would eventually become coal seams. This massive accumulation of carbon pulled so much CO2 from the atmosphere that global temperatures plummeted. Ice sheets spread. Sea levels dropped. The planet entered one of its longest ice ages, lasting tens of millions of years. Eventually, fungi evolved the ability to digest lignin, and the balance was restored. But for a long, cold stretch of Earth's history, trees were too successful, too enduring. They nearly froze the world with their own indestructibility. A tree's rings tell stories of the past. Slice through a fallen tree, and you'll see rings, concentric circles radiating out from the center. Each ring represents 1 year of growth. Wide rings mean good years, plenty of rain and warmth. Narrow rings mean drought, cold, or stress. But the story doesn't stop there. Scientists can read these rings like pages in a history book. They reveal not just the tree's life, but the climate of entire regions across centuries. Volcanic eruptions that cool the planet. Droughts that lasted decades. Wet periods that brought abundance. By matching ring patterns across many trees, living and dead, researchers have built continuous records stretching back thousands of years. Bristlecone pines in California have helped reconstruct climate data going back over 9,000 years. These silent witnesses hold memory in their wood, a living archive of seasons, storms, and survival. Some trees produce chemicals that smell like rain. You know that scent, fresh and clean, that rises from the earth after a summer rain. Part of it comes from trees. When rain hits dry soil, it releases a compound called geosmin, produced by soil bacteria. But trees contribute their own fragrance. Many trees, especially conifers, release volatile organic compounds called terpenes. When rain washes over needles and bark, these compounds are released into the air, mixing with moisture and other scents to create that distinctive smell of wet forest. Pine, cedar, fir, each has its own aromatic signature. Some of these compounds also play a role in cloud formation. The terpenes released by forests can help water vapor condense, seeding clouds and potentially influencing weather patterns. Trees don't just respond to rain. In a sense, they help create it, exhaling chemistry into the sky, calling moisture back to the earth. Trees can live without a single leaf. Deciduous trees shed their leaves every autumn, standing bare and still through winter. It might look like death, but it's strategy. Leaves are expensive to maintain. They lose water through tiny pores, and in winter, when the ground freezes, trees can't replace that lost moisture. So they drop their leaves, seal the wounds with protective layers, and wait. During this dormant period, trees are very much alive. Roots continue to grow slowly if the soil isn't frozen. Sap retreats deeper into the trunk, concentrated with sugars and compounds that act like antifreeze. Buds form tightly wrapped and waiting for spring. The tree breathes, but barely. It dreams in slow time, conserving energy, enduring cold. When warmth returns, the buds burst open in a matter of days, unfurling new leaves that will photosynthesize, grow, and thrive. The cycle begins again, ancient and reliable, a rhythm written into the very structure of life. Some trees bleed. When cuts slice into the bark of a dragon blood tree, and you'll see what looks like crimson sap oozing out. This resin, deep red and sticky, has been harvested for thousands of years and used as dye, medicine, and varnish. Other trees produce latex, a milky white fluid that flows when the bark is damaged. Rubber trees, for instance, have been tapped for centuries to collect this natural latex, which eventually becomes rubber. The fluid serves as a defense mechanism, sealing wounds and deterring insects with its sticky, sometimes toxic properties. These fluids aren't blood in the biological sense, but they serve a similar function. They protect, heal, and preserve. In the slow language of trees, this is how they respond to injury: flowing, sealing, enduring. A wound becomes a scar. The scar becomes part of the story. The oldest known tree is over 5,000 years old. High in the White Mountains of California, in a harsh, windswept landscape where few things grow, stands a bristlecone pine named Methuselah. It is over 4,150 years old, though its exact location is kept secret to protect it from vandalism. This tree was already ancient when the pyramids were built. It was centuries old when writing was invented. It has lived through every empire, every war, every human story we know, and it's still growing, slowly, adding narrow rings year by year. Bristle-cone pines thrive in poor soil and harsh conditions. Their wood is incredibly dense and resistant to decay. Even dead branches can remain intact for thousands of years, bleached white by sun and wind. These trees don't grow fast. They don't grow tall, but they endure, patient and silent, outlasting almost everything else on Earth. Trees can sense danger and defend themselves. When an insect begins chewing on a tree's leaves, the tree notices. It responds by producing chemical compounds that make its leaves less appetizing. Bitter tannins, toxins, or compounds that interfere with digestion. Some trees can even produce chemicals that attract predators of the insects attacking them, calling in reinforcements. Acacia trees in Africa take this a step further. When giraffes begin browsing on their leaves, acacias release ethylene gas into the air. Downwind trees detect this signal and start producing their own defensive chemicals before the giraffes even reach them. The giraffes have learned to move upwind or skip several trees to avoid this coordinated defense. Trees can't run, they can't hide, but they're far from helpless. In their own slow chemical language, they fight back, adapting, responding, surviving. A tree's roots, spread as wide as its branches, look up at a tree's canopy, the spread of its branches against the sky. Now imagine that same shape underground. In many cases, a tree's root system mirrors its crown, spreading just as wide, sometimes wider. Most tree roots don't grow deep. They spread outward, staying within the top few feet of soil where oxygen, water, and nutrients are most abundant. A large oak might have roots extending 50 feet or more in all directions, weaving through the soil, anchoring the tree against wind and storm. These roots do more than hold the tree in place. They sense moisture and grow toward it. They communicate with fungi. They absorb minerals and store energy. In winter, roots can grow even when the branches are dormant. Beneath the visible tree lies an entire hidden architecture, silent and essential. Some trees only reproduce after fire. In certain ecosystems, fire isn't destruction, it's renewal, and some trees have evolved to depend on it. Lodgepole pines, for instance, produce cones sealed shut with resin. These cones can hang on the tree for years, even decades, holding their seeds locked inside. Only when fire sweeps through the forest does the heat melt the resin, releasing the seeds onto freshly cleared, nutrient-rich soil. The parent tree may die, but its offspring sprout in the ashes, taking advantage of the sudden abundance of light and space. Eucalyptus trees in Australia have taken this even further. Their bark is rich in flammable oils, and they actively encourage fire. When flames race through, the trees drop burning bark, spreading the fire and clearing out competitors. Then they resprout from their trunks, green and vigorous, while other plants struggle to recover. Fire is part of the cycle, not an ending, but a beginning written in smoke and ash. Trees grow faster. When surrounded by others, you might think trees compete, each one fighting for light, water, and space, and to some extent they do. But studies have shown that trees in forests often grow faster and healthier than isolated trees, even when resources seem limited. Why? Because they help each other. Through underground networks, they share nutrients. Their combined root systems stabilize soil and retain moisture. Their canopies create microclimates, shading the ground and reducing evaporation. They even synchronize their growth, responding to the same seasonal cues. Isolated trees, despite having more light and space, often struggle. They face wind, temperature extremes, and soil erosion alone. They lack the fungal networks that connect forest trees. A tree in community is stronger than a tree in isolation. Together, they weather storms. Together, they thrive. A single oak can support thousands of species. An oak tree is never just an oak tree. It's an entire ecosystem. A mature oak can support over 2,300 species of insects, birds, mammals, fungi, lichens, and mosses. Beetles burrow into the bark. Caterpillars munch on leaves. Woodpeckers hammer into the wood, searching for larvae. Squirrels gather acorns. Bats roost in hollow branches. Lichens coat the trunk. Fungi grow on dead limbs. Owls nest in cavities. Ivy climbs toward the light. Each of these species depends on the oak, and many depend on each other. The oak provides food, shelter, and structure. It's not just a tree. It's a living tower of interdependence, a monument to the idea that one organism can hold a world within itself. Trees can warn each other of insect attacks. When a tree detects insect damage, it doesn't just defend itself, it sends out a warning. Using volatile organic compounds released into the air, the tree broadcasts a chemical signal that neighboring trees can detect. Upon receiving this signal, nearby trees begin producing their own defensive chemicals, even though they haven't been attacked yet. They're preparing, boosting their resistance, making themselves less appealing to herbivores. This airborne communication isn't limited to one species. Different tree species can understand each other's warnings. A willow under attack can alert nearby alders. A maple can warn an oak. It's a shared language of survival, invisible and quiet, drifting through the forest on the wind. Some trees store water in their trunks. In the dry regions of Africa, Madagascar, and Australia, baobab trees rise like giants with swollen, bulbous trunks. These trunks aren't just for structure, they're water tanks. During the rainy season, baobabs absorb and store thousands of gallons of water in their spongy wood. This reservoir allows them to survive months of drought, remaining green and alive when everything around them has withered. Elephants know this. In times of extreme drought, they've been observed tearing into baobab trunks to reach the water inside. These trees can live for over 2,000 years, slowly swelling as they age, their trunks becoming more massive and hollow. They're called the tree of life in many cultures, and it's easy to see why. In a harsh, unforgiving landscape, they hold water, provide shade, and offer fruit. They are survival-made wood. Trees can be bent but rarely break stand in a forest during a windstorm, and you'll see trees swaying, bending, flexing with the force of the wind. They don't resist rigidly, they adapt. Wood is both strong and flexible, a combination of cellulose fibers and lignin that allows it to bend without snapping. Trees grow in response to mechanical stress. If wind constantly blows from one direction, the tree thickens its trunk on the side facing the wind, building reinforcement where it's needed most. Even in hurricanes, most healthy trees survive by bending. Their roots anchor, their trunks sway, their branches give. It's the rigid, the brittle, the inflexible that break. Trees teach resilience not through resistance, but through movement, bending with the storm and standing again when it passes. Some trees can photosynthesize. Through their bark leaves are the primary organs of photosynthesis, but some trees don't stop there. Aspen and birch trees, among others, have chlorophyll in their bark, allowing them to photosynthesize even when leafless. This adaptation is especially useful in early spring or late fall, when leaves are absent but sunlight is available. The smooth, pale bark of these trees is designed to maximize light absorption. It's not as efficient as leaves, but it provides a small, steady source of energy during times when every bit counts. Even in dormancy, these trees are working, quietly converting sunlight into sugars, sustaining themselves through the lean seasons. The forest is never truly asleep. It only rests lightly, always ready to take advantage of warmth and light. Trees grow in two directions at once. Every year, a tree grows outward and upward. New wood forms just beneath the bark in a thin layer called the cambium. This layer adds rings to the trunk, making it thicker and stronger. At the same time, the tips of branches and roots grow longer, reaching toward light and nutrients. This dual growth happens simultaneously, a coordinated expansion in two directions powered by the same photosynthesis, the same flow of sap. In spring, growth is rapid. Cells divide quickly, producing light-colored porous wood. In late summer, growth slows. The wood becomes denser and darker. This creates the visible rings we see in cross-sections, a record of growth written in layers year after year, outward and upward, patient and unstoppable. Some trees can live underwater for months. Mangrove trees live where land meets sea, in brackish tidal zones where most plants would drown or die of salt exposure. But mangroves have adapted to thrive here. Their roots rise above the waterline, forming tangled arches that trap sediment and create new land. These aerial roots, called pneumatophores, allow the tree to breathe even when submerged at high tide. Salt is filtered out at the roots or excreted through special glands in the leaves. Mangroves are nurseries for fish, buffers against storms, and carbon sinks that store more carbon per acre than most terrestrial forests. They grow slowly, in difficult conditions, but they create ecosystems where none existed before. They are pioneers, standing at the edge of two worlds. A tree can sense gravity and grow accordingly. If a tree is knocked over or begins to lean, it doesn't simply accept its new orientation. It responds. Cells on the lower side of a tilted trunk grow faster, producing what's called reaction wood. This extra growth pushes the tree upright again. Trees sense gravity through tiny grains of starch inside their cells that settle downward. This simple mechanism allows them to detect which way is up and adjust their growth accordingly. Young trees bent by snow or wind will slowly straighten themselves over years. Even fallen logs can send up vertical shoots, reaching for the light. Trees are not passive. They adjust, correct, and reorient, always seeking the sun, always growing toward balance. Some trees drop their branches like lizards drop tails in times of extreme drought or stress. Some trees perform a dramatic act of self-preservation. They shed entire branches, allowing them to fall to the ground. This process, called cladoptosis, reduces the tree's overall water demand and energy expenditure. Eucalyptus trees are notorious for this. Large branches can drop without warning, sometimes weighing hundreds of pounds. It's a survival tactic, sacrificing part to save the whole. The fallen branches decompose, returning nutrients to the soil. The tree, now lighter and more efficient, can endure longer. When conditions improve, new growth begins. What looked like damage becomes strategy. What seemed like loss becomes adaptation. Trees can migrate over generations. Trees can't walk, but they can move. Over centuries, entire forests shift across landscapes, following changes in climate, advancing into new territory, retreating from old. This migration happens through seeds. A tree drops acorns, nuts, or wing seeds. Animals carry them. Wind disperses them. Water floats them downstream. Slowly, over generations, the population shifts. As the climate warms, many tree species are moving northward or to higher elevations, tracking the conditions they need to survive. Forests in Canada are creeping north. Alpine trees are climbing mountains. It's slow, often invisible within a human lifetime, but it's happening. Trees are on the move, one seed at a time. The hardest wood comes from the slowest growth. The strongest, densest wood doesn't come from fast-growing trees. It comes from those that grow slowly, adding narrow rings year after year. Ironwood, lignum vitae, ebony. These trees grow in harsh conditions where resources are scarce. Their wood is so dense it sinks in water. It's resistant to rot, incredibly hard, and has been used for tool handles, ship components, and fine instruments. Fast growth produces soft wood, light and porous. Slow growth produces durability. It's a trade-off written into the biology of trees. Patience creates strength. Time creates quality. In wood, as in life, the slow path often proves the strongest. Some trees have built-in fire alarms. Certain trees in fire-prone ecosystems have evolved to sense smoke. When smoke particles are detected, the tree triggers a stress response, closing its stomata, the tiny pores on leaves that allow gas exchange. This reduces water loss and helps the tree survive the heat and dryness that often accompany fire. Some pines even have serotinous cones that remain closed until exposed to the heat of fire, ensuring their seeds are released at the optimal moment for regeneration. These adaptations show that fire isn't an enemy to all trees. For some, it's an expected part of life, a force to be anticipated, responded to, and even used. The forest doesn't fear fire. It knows fire, and it has learned to dance with it. A tree's leaves are designed to catch light. Hold a leaf up to the sun. Notice its shape, its veins, the way it's positioned on the branch. Every detail is optimized for capturing light. Broad leaves maximize surface area. Needle-shaped leaves reduce water loss. Some leaves are waxy to reflect excess heat. Others are hairy to trap moisture. The arrangement of leaves on a branch follows mathematical patterns, spirals and angles that minimize shading and maximize exposure to sunlight. Chloroplasts inside the leaf cells are packed with chlorophyll, the molecule that absorbs light and converts it to energy. Every leaf is a tiny solar panel, evolved over millions of years to be as efficient as possible. And in autumn, when the chlorophyll breaks down, the other pigments hidden beneath are finally revealed. Gold, orange, crimson, a final blaze of color before the leaf lets go. Trees can survive being struck by lightning. Lightning strikes are violent and destructive, but many trees survive them. The sap inside the tree, full of water and minerals, conducts electricity better than the wood itself. When lightning hits, the current often travels down the outside of the trunk or through the moist cambium layer just beneath the bark. Sometimes a strip of bark explodes off in a spiral pattern as moisture inside flashes to steam. Sometimes the tree is scarred but remains standing, and sometimes, incredibly, there's little visible damage at all. Trees struck by lightning often develop unique growth patterns, forming burls or unusual grain in the wood. These lightning trees can live for decades or even centuries after the strike, carrying the mark of that violent moment like a scar, wounded but enduring. Some trees can recognize their own kin. Research has shown that some trees can distinguish between their own offspring and unrelated seedlings. Mother trees, connected through mycorrhizal networks, send more nutrients to their own young, supporting them preferentially. This isn't conscious choice, it's chemical recognition, a form of biological identity encoded in root, exudates, and signals pass through fungal threads. But the result is real, measurable favoritism. Trees support their genetic lineage, they invest in their descendants, and in doing so, they ensure not just their own survival, but the continuation of their particular adaptation, their resilience, their story. The forest is not just a community, it's a family bound by roots and recognition. A tree's bark is its armor. Bark is more than skin. It's protection, insulation, and transport all in one. The outer bark is dead tissue, corky and tough, designed to shield the living wood beneath from fire, insects, disease, and physical damage. Beneath the outer bark lies the inner bark, or phloem, which transports sugars from the leaves to the rest of the tree. Damage the bark all the way around the trunk, and you kill the tree by cutting off this flow. This is called girdling, and it's one of the few ways to kill a tree without cutting it down. Bark patterns are unique to each species. The deep furrows of oak, the smooth white of birch, the papery layers of eucalyptus. Each is adapted to its environment, to the threats it faces, to the life it lives. Bark is identity made visible, a signature written in texture and pattern. Trees can heal themselves. When a tree is wounded, cut, or damaged, it doesn't repair the injury the way animals do. It doesn't regenerate the lost tissue. Instead, it seals it off. The tree produces new growth around the wound, forming a callus of fresh wood that gradually covers the damaged area. Underneath, the old wound remains, but it's encased, isolated, prevented from spreading rot or infection to healthy tissue. This process is called compartmentalization. The tree builds walls, both chemical and physical, around the damage. It can't undo what happened, but it can contain it. Over years or decades, the wound disappears beneath layers of new bark, hidden but never forgotten. The scar becomes part of the tree's structure, a memory written in wood. Some trees produce fruit. That animals depend on oak trees produce acorns. Apple trees produce apples. Cherry trees produce cherries. These fruits aren't accidents, they're investments. A tree wraps its seed in nutritious, appealing flesh, designed to be eaten. Animals consume the fruit, digest the flesh, and excrete the seed, often far from the parent tree. The seed, protected by a hard shell and fertilized by the animal's waste, has a better chance of growing in a new location. This is mutualism. The tree provides food. The animal provides transportation and fertilizer. Both benefit. And over millions of years, this relationship has shaped both partners. Fruits became sweeter, more colorful, more attractive. Animals developed preferences, digestive adaptations, and behaviors that serve the tree's reproductive strategy. In every apple you eat, there's an ancient partnership written in sugar and seed. The largest living things are trees. The giant sequoias of California are the largest living organisms by volume. The biggest of them all, named General Sherman, stands 275 feet tall and contains over 52,000 cubic feet of wood. Its trunk alone weighs an estimated 1,385 tons. To stand at the base of General Sherman is to feel very small. Its bark is spongy and fire-resistant, sometimes over 2 feet thick. Its branches are themselves the size of large trees, and it's still growing, adding roughly 1 cubic meter of wood every year. These trees can live for over 3,000 years. They've survived countless fires, storms, and droughts. They are monuments not to strength alone, but to endurance, patience, and the slow accumulation of time made solid. In their presence, centuries feel like moments, and human life feels like the flutter of a single leaf. Trees can sense seasons through light and temperature. How does a tree know when to wake up in spring? It counts, not days, but light and warmth. Trees have photoreceptors that detect the length of daylight. When days grow longer, the tree begins preparing for spring. But day length alone isn't enough. Temperature matters too. If it's still freezing, the tree waits. This system prevents premature budding during warm spells in winter. The tree needs both signals, more light and sustained warmth, before it commits to growth. It's a built-in safety mechanism, refined over millennia of seasonal cycles. In autumn, the reverse happens. Shorter days and cooling temperatures trigger dormancy. Chlorophyll production stops. Leaves change color and fall. The tree withdraws inward, preparing for winter, not by thinking or planning, but by sensing and responding to the ancient rhythm of the turning year. Some trees can survive being cut down. Cut down a willow, and it doesn't die. Cut down a eucalyptus, and it sprouts again. Cut down an oak, and the stump may send up new shoots, a circle of young trees rising around the old base. This ability to re-sprout from stumps or roots is called coppicing, and it's been used by humans for thousands of years to sustainably harvest wood. The tree, or rather its root system, remains alive and continues to grow. Some coppice trees are incredibly old. Their above-ground parts may look young, but their roots are centuries old. In England, there are hazel and ash trees that have been cut and regrown for over 1,000 years, managed carefully, never allowed to fully mature, but never truly killed. It's a partnership between human and tree, based on the tree's remarkable resilience. Cut me, it seems to say, and I will grow again. Trees are the lungs of the earth. Every day, trees perform a quiet miracle. Through photosynthesis, they take in carbon dioxide and release oxygen. A single large tree can produce enough oxygen to support 2 people for a year. Globally, trees produce about 28% of the oxygen we breathe, with the rest coming from ocean phytoplankton. But trees do more than just make oxygen. They absorb carbon dioxide, storing carbon in their wood, leaves, and roots. Forests are massive carbon sinks, helping to regulate the planet's climate. When you breathe, you're participating in an exchange that includes every tree on Earth. The oxygen you inhale may have been released by a redwood in California, a rainforest tree in Brazil, or a birch in Scandinavia. With every breath, you're connected to forests you'll never see, trees you'll never touch, but trees that sustain you nonetheless. A tree's roots can break stone roots, may look delicate when they first emerge from a seed. thin white threads reaching into the soil. But over time, they become one of nature's most powerful forces. As roots grow, they expand, exerting tremendous pressure on their surroundings. They can crack stone, break concrete, and lift sidewalks. Ancient temples in Cambodia are slowly being torn apart by the roots of strangler figs and other trees that took root in cracks centuries ago. This isn't aggression, it's simply growth. The root follows the path of least resistance, seeking water and nutrients. If that path leads through a crack in rock, the root enters. As it thickens, the rock splits. Over years or decades, massive boulders can be broken apart by nothing more than patient, persistent growth. Trees are slow, but they are strong. Stone is hard, but it is brittle. Given enough time, the living always finds a way through the non-living. Some trees smell like vanilla or cinnamon. Walk through a grove of ponderosa pines on a warm day. Press your nose to the bark and breathe in. You'll smell vanilla or butterscotch or sometimes cinnamon. It's a sweet, warm scent, surprising and delightful. This aroma comes from compounds in the bark, released when warmed by the sun. Different trees, even different individuals of the same species, can smell slightly different. Some smell strongly, others barely at all. Sassafras trees smell like root beer. Black walnuts have a sharp, spicy scent. Cedar's aroma is fresh and clean, long used to repel moths and insects. These scents are chemical defenses, deterrents, and signals. But to us, wandering through the forest, they're gifts. An invitation to slow down, press close, and breathe deeply. Trees can weigh hundreds of tons. A large oak tree, fully mature, can weigh 50 tons or more. General Sherman, the giant sequoia, weighs an estimated 1,785 tons, but most of that weight is water. Fresh-cut wood is often 50% water by weight, sometimes more. The rest is cellulose, lignin, and other organic compounds. When wood is dried, it loses much of its mass. But while alive, the tree is full of sap, moisture drawn up from the roots and distributed throughout the trunk, branches, and leaves. This water is essential. It carries nutrients. It provides structural support. It cools the tree through evaporation. A tree isn't solid like stone. It's a living fountain, water flowing constantly upward, pulled by the evaporation of leaves in the canopy, a column of liquid rising hundreds of feet against gravity, held together by cohesion and the tree's own internal architecture. Heavy with life, heavy with water, heavy with time. Trees can create rain. In the Amazon rainforest, something remarkable happens. The trees don't just receive rain, they help create it. Through transpiration, trees release water vapor from their leaves. Billions of trees doing this simultaneously pump enormous amounts of moisture into the atmosphere. This water rises, cools, and condenses into clouds. Those clouds then release rain back onto the forest. It's a self-sustaining cycle. The forest makes its own weather. Scientists have found that air passing over the Amazon picks up more moisture than air passing over the ocean. The forest is so efficient at recycling water that rain can fall, be absorbed, transpired, and fall again multiple times as weather systems move across the continent. When forests are cut down, this cycle breaks. Rainfall decreases. Droughts become more common. The land dries. The forest doesn't just need rain to survive. In many places, the rain needs the forest. Some trees glow in the dark deep in tropical forests. There exists a phenomenon that seems like magic. Bioluminescent fungi grow on dead wood and tree bark, glowing with a soft, eerie light. This ghostly green glow is called foxfire, and it's been recorded in folklore and literature for centuries. The light comes from a chemical reaction similar to the one fireflies use. These fungi break down dead wood, digesting it and releasing this faint luminescence in the process. No one is entirely sure why they glow. It may attract insects that help disperse spores, or it may simply be a byproduct of their metabolism. Walk through certain forests at night, and you might see fallen logs glowing softly in the darkness, stumps radiating light, mushrooms gleaming like tiny lanterns. The forest, even in death and decay, finds ways to shine. A tree can be centuries old and still growing. Age doesn't stop a tree the way it stops most living things. Old trees don't become frail or weak. They just grow slower. A 500-year-old oak is still adding rings, still producing leaves, still making acorns. A 2,000-year-old sequoia is still reaching toward the sky. These ancient trees may have scars, hollow sections, dead branches, but their living tissue continues to function, continues to photosynthesize, continues to grow. In fact, some studies suggest that large, old trees grow faster in terms of absolute mass than younger trees. A 200-year-old tree might add more wood in a year than a 50-year-old tree, simply because it has more growing surface area in its cambium layer. Trees don't retire. They don't slow down and fade. They endure, adding year after year, ring after ring, as long as they have light, water, and soil. Age, for a tree, is not decline, it's accumulation. Trees can share nutrients with completely different species. The mycorrhizal networks that connect trees don't discriminate by species. A Douglas fir can share nutrients with a paper birch. An oak can support a pine. These trees may be competitors above ground, vying for light and space, but below ground, they cooperate. In experiments, researchers have tracked radioactive carbon as it moves from one tree to another through fungal networks. They've watched as older trees support younger ones, even when those young trees belong to different species. They've seen how trees in shade receive sugars from trees in sunlight. This generosity defies simple evolutionary logic. Why help a competitor? Yet it happens consistently across forests worldwide. Perhaps because the forest's survival benefits all trees. Perhaps because the fungal networks themselves broker these exchanges. Or perhaps because cooperation, at the level of ecosystems, is simply more successful than pure competition. The forest teaches a quiet lesson. Thriving isn't about winning, it's about connection. Some trees drop their seeds like helicopters. Watch a maple seed fall, and you'll see it spin. Those paired wings, called samaras, helicopter down from the tree, spinning rapidly and slowing the seed's descent. This design maximizes the time the seed spends in the air, giving wind more opportunity to carry it away from the parent tree. Some maple seeds can travel hundreds of feet before touching ground. The spin stabilizes the flight, preventing tumbling or dropping straight down. Other trees have their own dispersal strategies. Dandelion seeds float on feathery parachutes. Pine seeds have papery wings. Coconuts float across oceans. Burrs stick to fir. Each method reflects the tree's environment and the partners, wind, water, or animals, it relies on to spread its offspring. Seeds are small packages of potential, And trees have evolved thousands of ways to ensure those packages travel far from home, to new soil, new light, new chances. Trees can live on almost nothing. In the harshest environments, trees survive on what seems like barely anything at all. Bristlecone pines cling to rocky slopes where soil is thin and poor. Desert acacias send roots deep into sand, searching for underground moisture. Mangroves filter salt from seawater. These trees grow slowly. Their wood is dense. Their leaves are small or waxy or needle-thin, designed to conserve every drop of water. They may add only a few millimeters of growth per year, but they persist. The secret isn't abundance, it's efficiency. These trees waste nothing. Every resource is used, recycled, conserved. They've learned to thrive not despite scarcity, but because of the adaptations scarcity forced them to develop. In poor soil, with little water, under harsh sun or bitter cold, these trees endure, not flourishing in the way we might imagine, but alive, patient, and quietly victorious. A forest floor is never silent. Stand still in a forest and listen. Really listen. Beneath the obvious sounds, the birds and wind, lies a quieter orchestra. Leaves rustle as they fall. Insects hum and click. Branches creak. Acorns drop with soft thuds. Water drips from leaf to leaf after rain. Fungi release spores in tiny puffs. Roots shift and crack soil as they grow. Animals move through underbrush, careful or careless. And beneath all of it, too quiet to hear without special equipment, is the sound of trees themselves, the flow of sap, the opening and closing of stomata, the slow expansion of cells. Some researchers have recorded the ultrasonic clicks of xylem conduits snapping under drought stress, the tree's equivalent of thirst. The forest is never silent. It breathes, it moves, it speaks. You just have to slow down enough to listen. Trees can be shaped by humans for centuries. In Japan, the art of bonsai has been practiced for over 1,000 years. These miniature trees, carefully pruned, wired, and trained, can live for centuries in shallow pots. They're not different species. They're normal trees, kept small through constant care. Their roots are trimmed. Their branches are guided. Their growth is slowed but not stopped. A bonsai pine might be 300 years old, no taller than your forearm, but still alive, still growing, still making tiny cones. Similarly, pleach trees in European gardens are trained to grow in flat plains, their branches woven together to form living fences or archways. This shaping takes years of patient work, bending and binding young wood before it hardens. Trees are flexible, not just in body, but in form. With time and care, they can be guided into shapes nature never intended. And they accept this guidance, adapting, growing within the constraints given, proving once again that trees are masters of endurance and adaptation. The smell of cut grass is a tree's cousin, that fresh, green scent when grass is mowed. Those are volatile organic compounds being released, chemical distress signals. Trees do something similar. When injured or stressed, many trees release terpenes and other compounds into the air. Some smell pleasant to us, like pine or citrus. Others are barely detectable. But to other organisms, these scents carry information. Some attract beneficial insects. Others warn nearby trees. Still others deter herbivores. The smell of a forest, rich and complex, is a chemical conversation. Every scent is a message. The resinous aroma of conifers, the sweet decay of fallen leaves, the sharp tang of broken branches, all of it is communication, defense, and chemistry, woven into the air itself. We walk through this invisible language every time we enter the woods, breathing in messages not meant for us, but beautiful nonetheless. Some trees are planted by squirrels. Who forget squirrels gather acorns and nuts in autumn, burying them in scattered locations for winter food. They have remarkable spatial memory and can relocate many of these caches months later, but not all of them. The forgotten acorns, buried in good soil and left undisturbed, sprout. These squirrel-planted trees grow in patterns shaped by squirrel behavior, often near trails, stumps, or landmarks the squirrel used for navigation. In this way, squirrels are among the forest's most important tree planters. They don't intend to plant forests, they're just storing food. But their imperfect memory becomes the forest's gain. Forgetfulness becomes creation. An abandoned cache becomes an oak. It's a partnership neither party planned, evolved over millions of years, binding the fate of trees to the appetites and habits of small, forgetful mammals. Trees can sense. When they're being eaten, when a caterpillar begins chewing a leaf, the tree responds within minutes. It detects the chemical signature of the caterpillar's saliva, distinguishing it from simple mechanical damage like wind or hail. This specific recognition triggers a targeted defense. The tree produces enzymes that make digestion harder for the caterpillar. It releases volatiles that attract parasitic wasps, which lay eggs in the caterpillar. Some trees even warn neighboring trees through airborne signals. The response is precise and adaptive. Different herbivores trigger different defenses. The tree knows what's eating it and responds accordingly. This isn't consciousness, but is far more sophisticated than we once believed. Trees are not passive. They're reactive, responsive, constantly monitoring and adjusting. They live in conversation with everything that touches them. Fallen logs feed the forest for decades. When a tree falls, its life isn't over. It's transformed. The log becomes habitat for insects, fungi, mosses, and small animals. As it slowly decomposes, it releases nutrients back into the soil, feeding the next generation of trees. These nurse logs are especially important in old-growth forests. Seedlings sprout from them, their roots reaching down through the rotting wood into the soil below. Rows of trees can grow from a single fallen giant, standing like guardians along the body of their ancestor. The decomposition can take centuries. A large Douglas fir log might persist for 200 years, slowly breaking down, layer by layer. In that time, it will have sheltered thousands of organisms, fed countless others, and supported the growth of dozens of new trees. Death in the forest is never an ending. It's a continuation, a transformation, a gift passed forward. Trees can survive with hollow trunks. Ancient trees often develop hollow centers. Disease, fire, or insects excavate the heartwood, leaving the tree with a hollow core, sometimes large enough to stand inside. Yet these trees survive. The living tissue, the sapwood and cambium, lies just beneath the bark. That's where water and nutrients flow. The heartwood in the center is dead tissue, providing only structural support. Remove it, and the tree becomes weaker, but doesn't die. Some hollow trees live for centuries more, their shells of living wood continuing to grow outward, even as the center remains empty. They become refuges for owls, bats, raccoons, and countless other creatures seeking shelter. A hollow tree teaches a profound lesson. What's essential to life is often at the edges, in the growing layer, in the active boundary between inner and outer. The center can be emptiness, and still, life continues. Some trees only release seeds every few years. Oaks, beeches, and many other trees don't produce seeds consistently every year. Instead, they participate in massed years, synchronized events where entire forests produce massive crops of seeds all at once. These massed years occur irregularly, every 2 to 5 years, triggered by weather patterns and internal signals. When they happen, the ground becomes carpeted with acorns or beech nuts, far more than animals can eat. This strategy overwhelms seed predators. In non-massed years, squirrels and birds eat nearly every seed, but in massed years, so many seeds are produced that even after animals gorge themselves, thousands remain to germinate. It's survival through abundance and timing. The forest coordinates this boom and bust cycle across species and distances. 1 year of plenty followed by years of scarcity, a rhythm that benefits the trees and shapes the entire ecosystem's population dynamics. Your desk, your floor, your home hold stories. Look at the wood around you, the table, the floor, the bookshelf. Each piece was once part of a living tree. Each ring in that wood represents a year, a season, a period of growth. The oak in your floor may have been 150 years old when it was cut. It witnessed weather patterns, survived droughts, endured storms. The wood you touch every day holds that history, silent and still, transformed from living tissue into human use. We often forget this connection. Wood feels inert, lifeless, but it was alive. It grew, it breathed, and now it serves a new purpose, shaped by human hands but carrying still the structure, the patterns, the memories of its time as tree. In every wooden object lies a small piece of forest, a fragment of something ancient and patient, brought into our homes and lives. 50. Facts about trees to fall asleep. 2. Continuation. Facts. 51. 99. Trees can remember drought. When a tree experiences severe drought, something remarkable happens in its cells. It doesn't just survive and forget, it remembers. Years after a drought has ended, trees that experienced it show different growth patterns than those that didn't. They're more conservative with water, closing their stomata earlier in the day. They invest more in root growth relative to shoots. This isn't genetic change, it's epigenetic memory, chemical markers that alter how genes are expressed without changing the DNA itself. Some of these changes can even be passed to the next generation through seeds. A tree that survived drought produces offspring slightly better prepared for water scarcity. Experience becomes adaptation. Hardship becomes wisdom, written in chemistry and passed forward through time. Some trees can walk in the rainforests of Central and South America. Grows a palm tree that seems to defy everything we know about trees. The walking palm, Socratea exoryza, sends out new roots from its trunk, extending away from its base. Over time, as these stilt-like roots establish themselves and old roots die, the tree's position shifts. It doesn't walk quickly, perhaps a few centimeters per year, but it moves. Scientists believe this allows the tree to reposition itself toward better light or away from obstacles. Not all researchers agree that it truly walks, and the movement is certainly slow, but the image is irresistible. A tree with roots like legs, taking patient steps through the jungle, one root at a time, moving through the forest as if searching for something just beyond reach. A tree's flowers can bloom for just one day. The baobab tree produces magnificent flowers, large and white, hanging from long stalks. They smell sweet and musty, designed to attract their pollinators, bats. But these flowers are ephemeral. They open at dusk and bloom through the night. By morning, they've already begun to wilt. By the end of the next day, they've fallen. Each flower exists in full glory for less than 24 hours. This brief blooming is common among bat-pollinated plants. Bats are efficient pollinators, visiting many flowers in a single night. The tree needs only provide its flowers for one evening. Why invest more energy than necessary? Its efficiency and beauty combined, a spectacular display that exists in the boundary between sunset and sunrise, then fades like a dream. Trees can drown. We think of plants as needing water, but trees can have too much of a good thing. Roots need oxygen to function, to produce energy, to grow. When soil becomes waterlogged and stays that way, oxygen is displaced. The roots suffocate. Different trees have different tolerances. Willows and cypresses thrive in wet conditions, having adapted special root structures that can function with less oxygen. But most trees, if their roots are submerged for weeks, will die. You can see this after floods. Healthy trees suddenly turn brown, their leaves wilting despite being surrounded by water. It's not lack of water killing them, it's lack of air. Even trees, those symbols of endurance, have limits. Even they can have too much of what they need. Some trees produce antifreeze. In regions where winter temperatures plunge far below freezing, trees face a deadly problem. Ice crystals forming inside cells can puncture cell walls and kill living tissue. So trees make antifreeze. They produce sugars, proteins, and other compounds that lower the freezing point of water inside their cells. Some can survive temperatures of 40 degrees or lower. The sap becomes concentrated, almost syrupy, resistant to freezing. But there's a limit. In the coldest parts of the world, trees simply can't survive. The Arctic tundra has no trees, not because of lack of summer warmth, but because winter cold exceeds what even the hardiest tree can endure. There's a tree line at high latitudes and high elevations, a boundary beyond which even chemistry and adaptation cannot go. The trees stop there, marking the edge of what's possible. A tree can support its own weight through tension. How does a 300-foot tall redwood lift water from its roots to its highest leaves? Pumps would require enormous energy, but the tree does it passively through tension. As water evaporates from leaves, it creates negative pressure, a pulling force. Water molecules stick together through cohesion, forming continuous columns in the tree's xylem vessels. The evaporation at the top pulls the entire column upward, like sucking through an enormous straw. This tension is immense. The water columns are under such negative pressure that they should theoretically vaporize, forming bubbles that would break the flow. But they don't. The narrow vessels and the water's cohesion keep the columns intact. It's one of nature's most elegant engineering solutions. No moving parts, no energy expenditure beyond what the sun provides for evaporation, just physics, chemistry, and the patient architecture of wood, lifting water hundreds of feet into the air, defying gravity through tension alone. Trees can lose half their branches and survive. A severe ice storm can strip a tree of massive amounts of its structure. Half its branches might break and fall. You'd think this would be fatal, a catastrophic injury. Often, the tree survives just fine. Trees are modular organisms. Each branch is somewhat independent. Lose some branches, and the remaining ones compensate. They grow more vigorously, their leaves working harder. The tree redirects resources to what remains. Within a few years, you might not even notice the damage. New growth fills in gaps. The canopy recovers. The tree, though scarred, returns to function. This modularity, this redundancy built into the tree structure, is part of what makes them so resilient. They're not single, fragile entities. They're collections of semi-independent parts that can lose some elements and still thrive. Some trees have been to space seeds. From various tree species have been carried into space and returned to Earth. Moon trees, grown from seeds that orbited the moon aboard Apollo 14 in 1971, have been planted across the United States. These trees grew normally, showing no obvious differences from Earth-bound seeds. The brief exposure to space conditions and lunar orbit didn't alter them in detectable ways. They're living connections to human space exploration, rooted in Earth but carrying the memory of having touched the edge of the cosmos. There's something poetic about it. Trees, those ancient rooted beings traveling to the moon. Seeds that crossed the void between worlds, then germinated in familiar soil, growing as trees have always grown, connecting ground and sky. A tree's shadow helps other trees. In a dense forest, you might think the trees on top, those with full access to sunlight, would benefit most. But the canopy trees also create conditions that help the entire forest. Their shade keeps the forest floor cool and moist. It prevents soil from drying out. It protects seedlings from harsh sun that would desiccate them. The leaf litter from canopy trees feeds fungi and builds soil. Their roots stabilize hillsides, preventing erosion that would wash away nutrients. A forest's health depends on its layers. The emergent trees, the canopy, the understory, the forest floor, all are interdependent. The tallest trees give shade, not competition. They create the conditions in which the next generation can grow. Dominance becomes stewardship. Success creates opportunity for others. Trees can sense touch brush repeatedly against a young tree, and it will respond. It will grow shorter and stockier with a thicker trunk. This phenomenon is called thigmomorphogenesis, growth in response to mechanical stimulation. Trees sense wind, rain, and the touch of passing animals. These stimuli trigger genes that alter growth patterns, making the tree more resistant to physical stress. A tree grown in a greenhouse, never exposed to wind, will be tall but weak. A tree grown outside, constantly buffeted, will be shorter but much stronger. This response is so sensitive that even regular gentle touching can trigger it. Trees feel their environment and adjust their growth accordingly. They're not just growing toward light, they're responding to every force that touches them, building themselves to match the world they live in. Some trees produce flowers before leaves in early spring. Some trees bloom while their branches are still bare. Magnolias, cherries, redbuds, they burst into flower before a single leaf unfurls. This timing isn't accidental. Flowers need pollinators. When leaves aren't in the way, the flowers are more visible to insects and birds. The energy for flowering comes from reserves stored in the trunk and roots from the previous year. There's something especially beautiful about a bare tree covered in blossoms. The flowers seem impossible, too delicate for the stark branches, too vivid against grey wood. But there they are, pink and white against brown. Proof that life persists even when it seems dormant, that beauty can emerge from what looks like lifelessness. A tree's roots, can fuse with neighboring roots. Sometimes, when roots from different trees meet underground, they don't just touch, they fuse. The bark breaks down where they press together, and the living wood merges into a single structure. This root grafting creates physical connections between trees. Water and nutrients can flow between them. Sometimes, when one tree is cut down, its stump continues to live for years, kept alive by nutrients flowing from neighboring trees through these grafted roots. Scientists have found extensive root grafting networks in many forests. Trees aren't just connected by fungal networks. Sometimes their very bodies join, wood to wood, creating a physical union that transcends individual identity. The forest becomes more connected, more literally unified than we ever imagined. Trees can alter soil chemistry. Beneath a pine tree, the soil is acidic. Beneath an oak, it's more neutral. Trees don't just adapt to their soil, they change it. Pine needles, when they decompose, release acids. Oak leaves are more neutral. As these materials break down year after year, they alter the pH and nutrient composition of the surrounding soil. Over time, a tree creates conditions that favor itself. Some trees take this further. Black walnut produces juglone, a chemical that inhibits the growth of many other plants. It creates a zone around itself where competitors struggle. The walnut shapes its environment chemically, ensuring it faces less competition. This ability to engineer soil means trees don't just find suitable habitat, they create it. They're not just inhabitants of their environment, they're architects of it, shaping the ground beneath them to suit their needs. Some trees need fire to release their seeds. We've touched on this, but it bears deeper reflection. Imagine being a tree whose entire reproductive strategy depends on fire, on the very force that might kill you. Jack pines and lodgepole pines evolved this strategy in fire-prone ecosystems. Their cones are sealed with resin, sometimes staying closed for decades. Only intense heat melts the seal, releasing seeds onto ash-fertilized soil at the exact moment when competition has been cleared away and nutrients are abundant. It's a dramatic gamble. The parent tree often dies, but its offspring inherit a cleared, fertile landscape. Natural selection favored trees willing to sacrifice themselves for their offspring's advantage. In harsh environments, extreme strategies become necessary. The trees that survived were those that made fire part of their life cycle. Not an enemy to fear, but a partner in reproduction. A tree can be hollow and still strong. Ancient oaks and chestnuts sometimes become hollow with age. Their heartwood rotted away, leaving only a shell of living wood surrounding an empty core. These hollow trees can still be structurally sound. The outer layers, where living tissue resides, continue to grow and strengthen. The hollow center, once structural support, becomes unnecessary as the tree develops its strength in the expanding circumference. Some hollow trees are large enough inside for people to enter. One famous oak in England had a door installed and served as a small dwelling. Another was large enough to hold several people standing. These trees demonstrate that strength doesn't always mean solidity. Sometimes it's in the shell, the surface, the boundary between inner and outer. Sometimes emptiness at the center doesn't mean weakness. It just means the strength has moved to the edges. Trees can make their own rain. Through chemistry beyond transpiration, trees influence weather through chemistry. They release organic compounds that serve as cloud condensation nuclei, tiny particles around which water vapor condenses to form clouds. In the Amazon, these tree-produced compounds are so abundant that they significantly affect regional weather patterns. The forest doesn't just recycle moisture, it actively creates conditions for cloud formation and precipitation. This means that forests, especially tropical ones, are not just affected by climate. They help create it, remove the trees, and rainfall patterns shift. The climate changes. The forest and the weather are locked in mutual dependence, each creating conditions for the other. A cycle that took millions of years to establish and can be broken in decades. Some trees can live partially dead. Lightning strikes, disease, or damage can kill part of a tree while leaving other parts alive. You'll see trees with one half of their trunk dead, bark sloughed off, wood bleached white. The other half remains green and growing. This partial death can persist for centuries. The living side continues to photosynthesize, grow, and produce leaves. The dead side remains, weathered but present, a scar that never fully heals but doesn't spread. These half-dead trees are haunting and beautiful. They're visual reminders that death and life can coexist in the same organism, that survival sometimes means accepting loss, carrying damage forward, and continuing despite being incomplete. A tree's age can be read in its shape. Foresters and naturalists learn to estimate a tree's age without counting rings. They read it in the tree's form. Young trees grow rapidly upward, their branches reaching skyward at sharp angles. Middle-aged trees have spreading crowns, branches extending widely. Old trees often have flattened or rounded tops, their highest branches dead or dying, their growth slowed. The bark changes too. Smooth in youth, deeply furrowed in age. The trunk thickens. The ratio of canopy to trunk shifts. An experienced observer can look at a tree's silhouette and estimate its age within decades, reading time in form, in proportion, in the story written in branch and bark. Trees can survive with roots severed when construction cuts through a tree's root system or a trench is dug nearby. Major roots can be severed. This is often fatal, but sometimes, surprisingly, the tree survives. The remaining roots work harder, growing more rapidly, taking up more water and nutrients. The tree may reduce its canopy, dropping leaves or failing to produce as much new growth, conserving resources while the root system regenerates. Trees have remarkable capacity to compensate for injury. They can't heal severed roots, but they can grow new ones. They can adjust their water use, their growth rate, their entire physiology to match diminished capacity. It's adaptation in real time, resilience made visible. Some trees drop poisoned leaves. In autumn, before leaves fall, trees withdraw valuable nutrients from them, reabsorbing nitrogen, phosphorus, and other compounds to recycle for next year. What's left behind are the materials the tree doesn't need. Some trees, including eucalyptus and black walnut, leave toxic compounds in their fallen leaves. As these leaves decompose, they release chemicals that inhibit seed germination and plant growth beneath the tree. This chemical warfare through leaf litter reduces competition. It creates a zone of control where the tree faces fewer challenges for water, nutrients, and light. Even in death, the leaves serve their tree, providing one last service, protecting their parents' territory with poison. A tree can recognize danger before it arrives. Research has shown that trees can detect the vibrations created by insects chewing on their leaves. Different insects create different vibration patterns, and trees can distinguish between them. Upon detecting these vibrations, trees ramp up their chemical defenses specifically tailored to the type of attacker. It's not just response to damage, it's anticipatory defense based on identifying the threat. This means trees have a kind of hearing, a way of sensing danger through vibration, through the physical waves of energy that travel through their tissues. They listen to the forest, to the insects on their leaves, and they respond to what they hear. Trees can store memories in their wood. A tree's wood records more than just its age. It records events. A fire leaves char. Floods leave watermarks. Physical damage creates irregular growth patterns around wounds. Scientists can read these records. They can identify the year a fire swept through by finding the layer of damaged wood. They can see when insects infested a forest, when a drought occurred, when unusual weather patterns emerged. The tree remembers, not in neurons or consciousness, but in wood. Its body is an archive, each ring a page, each scar a footnote. The tree carries its history physically, literally, in the substance of itself. Some trees have thorns that house armies. Acacia trees in Africa grow long, hollow thorns. But these aren't empty. They're homes. Entire colonies of ants live inside, thousands of individuals in a single tree. This is mutualism at its most dramatic. The tree provides shelter. The ants provide defense, swarming out to attack any animal that touches the tree. Giraffes, elephants, insects, all face the fury of these ant colonies. The ants are so committed that they'll prune any vegetation that grows too close to their acacia, ensuring it faces no competition. They'll even attack the tree's own shoots if they shade too much. The partnership is ancient and intricate, written into the behavior of ants and the chemistry and structure of the tree. A tree can be its own ecosystem. We've talked about the species a tree supports, but the full number is staggering. A single mature tree can be home to thousands of species, many of them microscopic. Bacteria live on and in the bark. Fungi colonize the wood. Lichens coat the trunk. Mosses grow on branches. Ferns sprout in crevices. Insects bore, nest and hunt. Birds nest. Mammals den. Reptiles bask. Amphibians shelter. Each of these organisms interacts with others, creating food webs, predator-prey relationships, and symbioses. The tree isn't just habitat, it's the foundation of an entire community, a living tower that creates complexity through its mere existence. Trees can bend light to walk through a dense forest and notice the quality of light. It's green-tinted, filtered through layers of leaves. This filtering isn't just aesthetic. It changes what plants below can use. Trees absorb red and blue light for photosynthesis, reflecting and transmitting mostly green. Plants on the forest floor have adapted to photosynthesize with this filtered, green-heavy light. They're using the leftovers, the wavelengths the canopy trees don't need. In some forests, only about 2% of sunlight reaches the forest floor. Plants there have evolved extreme shade tolerance, able to survive and grow on this fraction of light. The canopy bends light to its needs, and everything below must adapt to the altered spectrum that remains. Some trees bloom. Only at night tropical trees like the calabash tree produce flowers that open only after sunset. They bloom white or pale, visible in darkness, and produce strong, often unpleasant scents, musty or fermented. These are bat flowers, designed to attract nectar-feeding bats. Bats don't need bright colors. They navigate by echolocation and are drawn by scent, so the flowers maximize scent and minimize daytime display, saving energy by not maintaining blooms that diurnal pollinators would never visit. In the darkness of the tropical forest, these trees offer their blooms to flying mammals, an exchange that happens in night's privacy, unseen by most humans, a testament to the countless interactions that shape forests in ways we rarely witness. A tree can change its offspring's chances when a tree experiences stress, attacked by insects, drought, or disease. It doesn't just defend itself, it alters the chemistry of its seeds. Offspring produced during times of stress emerge with enhanced defenses, thicker leaves, more chemical deterrents, better drought tolerance. This isn't genetic mutation. It's epigenetic priming, chemical markers that alter gene expression. The mother tree is, in effect, warning its offspring about the challenges they'll likely face, preparing them before they even germinate. It's anticipatory adaptation, a way of giving the next generation an advantage based on current conditions. The tree can't change its genes quickly, but it can adjust how those genes are expressed in its offspring, providing them with an edge. Trees can form natural bridges. In certain parts of India and Southeast Asia, people have cultivated living bridges from the aerial roots of rubber fig trees. These roots naturally grow downward from branches, seeking soil. People guide them across rivers and gaps, training them where to grow. Over years, the roots thicken and strengthen. They fuse together. Eventually, they become strong enough to support human weight, then many humans. Some of these living bridges are centuries old, still growing, still strengthening, still functional. They require no maintenance beyond occasional weeding. They get stronger with age rather than weaker. They're self-repairing and immortal as long as the tree lives. They're infrastructure that's alive, that grows, that improves with time rather than degrading. Some trees can count fruit trees, need a period of cold before they'll bloom in spring. They need to know winter has happened, so they count cold days. Through complex chemical processes, trees track exposure to temperatures below a certain threshold. Once they've accumulated enough chill hours, they're ready to bloom when warmth arrives. This prevents them from flowering during brief warm spells in winter, which would doom the flowers to frost. Different species need different amounts of cold. Apples need 800 to 1,200 hours. Peaches need 600, 900. The tree keeps a chemical tally, marking time in a molecular ledger, ensuring it blooms only when the danger of hard frost has truly passed. A tree's flowers can be male or female or both. Some tree species produce separate male and female flowers. Others produce perfect flowers, containing both male and female parts. Some trees have all male flowers or all female, with the opposite sex on different individual trees. This diversity of strategies reflects different evolutionary solutions to the problem of reproduction. Separate male and female trees prevent self-pollination, ensuring genetic diversity. But it means both sexes must be present for reproduction. Perfect flowers can self-pollinate in isolation, but risk inbreeding. Some trees even change sex over their lifetime, starting as male and becoming female with age, or vice versa. The biology of tree reproduction is far more complex than simple pollination. Its strategy, timing, chemistry, and genetic innovation shaped over millions of years. Trees can survive being eaten. Deer browse trees in winter, eating twigs and bark. Rabbits gnaw on young saplings. Insects devour leaves. Yet most trees survive this constant consumption. They've evolved to tolerate herbivory to a degree. They overproduce leaves, branches, and bark, expecting to lose some. They can regrow from buds, sprout from roots, and seal wounds. Up to a certain threshold, the damage is manageable. Factored into the tree's growth strategy, it's when herbivory exceeds this threshold, when deer populations explode or insects swarm in unusual numbers, that trees die. But under normal circumstances, being eaten is just part of life. The tree accepts the loss and continues, damaged but functional, scarred but alive. Some trees explode to spread seeds. The sandbox tree of tropical America has earned a dramatic nickname, the dynamite tree. When its fruit ripens and dries, internal pressures build. Eventually, the fruit explodes, sometimes with a sound like a gunshot, flinging seeds up to 150 feet away at speeds over 160 miles per hour. Other trees have less violent but equally clever dispersal mechanisms. Witch hazel capsules contract as they dry, eventually snapping and shooting seeds several yards. Its ballistics powered by nothing but drying tissue and mechanical tension. These trees turn their fruit into spring-loaded launchers, ensuring seeds travel far from the parent. No wind needed, no animals required, just physics, patience, and the explosive release of stored energy. A tree can wait decades to bloom. Some trees, especially those in harsh environments, can grow for decades before producing their first flowers. Bamboo, technically a grass but growing tree-sized, can grow for 50 to 100 years before flowering. This delayed reproduction reflects a calculation. The tree invests in growth, in establishing deep roots, in building reserves, before attempting the energetically expensive process of flowering and seed production. When flowering finally comes, it's often spectacular. Some bamboos flower synchronously. Entire groves blooming at once after decades of vegetative growth. Then, having flowered and set seed, they die. The offspring germinate in the cleared space, beginning the cycle again. Trees can sense gravity to stay upright. Inside every tree cell are tiny grains of starch called statoliths. These grains settle to the bottom of cells due to gravity. The tree senses their position and uses this information to determine which way is up. If the tree begins to lean, cells detect the changed position of statoliths and respond by growing more on one side, pushing the tree back toward vertical. This response is constant and automatic, an ongoing adjustment that keeps the tree upright throughout its life. Even individual branches sense gravity and adjust their growth, maintaining optimal angles for light capture and structural integrity. The tree is constantly sensing, calculating, and adjusting its form in response to the fundamental force that shapes everything on Earth. Some trees weep. Sap birch trees, when tapped in late winter or early spring, will flow with sap. Not a trickle, a flood. A healthy birch can yield several gallons in a day. This sap is mostly water with dissolved sugars, flowing from roots to branches as the tree prepares for spring growth. The pressure is positive, pushed by root pressure rather than pulled by evaporation. Tap the trunk, and the tree literally weeps. This sap has been harvested by humans for thousands of years, drunk, fresh, or fermented. The tree can tolerate the tapping if done carefully, sealing the wound once the tap is removed. It's another example of trees' remarkable generosity, providing sustenance to other species, sometimes to their own detriment, but more often surviving the taking and continuing on. A tree's leaves can track the sun. Some trees have leaves that move to track the sun throughout the day, a behavior called heliotropism. They angle themselves to maximize light capture in the morning and evening, and sometimes turn edge-on at midday to avoid overheating. This movement is controlled by changes in turgor pressure in cells at the base of the leaf stem. It's not as dramatic as the movement in sunflowers, but it's measurable. The leaves are always optimizing, always adjusting to make best use of available light. This constant adjustment means the tree is actively engaged with its environment every moment. It's not static, not passive. It's responding, moving, optimizing, alive in ways we rarely notice, but which are essential to its success. Trees can grow on other trees. Epiphytes, plants that grow on other plants, are common in tropical forests. Orchids, ferns, and bromeliads sprout in the crooks of tree branches, high in the canopy. These aren't parasites. They don't take nutrients from the host tree. They collect water and nutrients from rain, dust, and decaying matter that accumulates around them. The host tree provides only physical support, a platform closer to light. Some epiphytes grow so abundantly that they significantly increase the weight a tree must support. In tropical cloud forests, trees can be laden with hundreds of pounds of epiphytic growth. Yet most trees tolerate this, their strength sufficient to support not just themselves, but entire gardens of other species living in their branches. Some trees grow knees. Bald cypress trees, growing in southern swamps, produce unusual structures called cypress knees. These are extensions of the root system that grow upward, breaking through the water's surface. Their exact function is still debated. They may help with gas exchange, allowing oxygen to reach roots in waterlogged soil. They may provide structural support in soft mud. They may serve both functions or others not yet understood. These knees give swamps a surreal appearance, wooden spikes rising from dark water, testimony to the tree's adaptation to life in a flooded environment. Their problem-solving made visible, evolution's response to a specific challenge rendered in wood. A tree can be cloned from a single cell. In laboratories, scientists can take a single cell from a tree and culture it, growing a complete new tree that's genetically identical to the parent. This technique, called micropropagation, allows rare or valuable trees to be reproduced rapidly. The process reveals something profound about trees. Every cell, even those in bark or wood, contains the complete genetic blueprint for the entire organism. Given the right chemical signals, that cell can become root, shoot, leaf, or flower. This totipotency, this potential for any cell to become a whole organism, shows that trees are not just colonies of cells, but rather one cell repeated millions of times, each capable of becoming the whole. Trees can filter air beyond producing oxygen. Trees remove pollutants from the air. They absorb gases like nitrogen dioxide, sulfur dioxide, and ozone through their stomata. Particles like dust, ash, and pollen stick to leaves and bark. A single mature tree can absorb dozens of pounds of pollutants annually. Urban forests significantly improve air quality, filtering the air that millions of people breathe. The leaves that do this filtering eventually fall, taking the absorbed pollutants with them into soil where many are broken down or bound up. The tree is a living air purifier, working constantly, asking nothing in return, cleaning the atmosphere simply by existing. Some trees can fossilize while standing in certain volcanic regions. Trees can be buried by ash and mud while still upright. The organic material gradually replaces with minerals, cell by cell, creating a perfect stone replica of the original wood. These petrified forests preserve not just the shape but the internal structure of trees. You can see individual cells, growth rings, even insect borings, all turned to stone. They're windows into ancient forests, showing us trees that lived millions of years ago, now harder than the rocks around them. In life, the tree was soft, flexible, alive. In death, it became eternal, transformed from carbon-based life to silicon-based remembrance, proof that even death can be a kind of transformation rather than ending. A tree's buds contain next year's growth. When you see buds form in late summer and autumn, you're seeing next year's leaves and flowers, already formed, just waiting. Inside those tight scales are miniature leaves, perfectly shaped, compressed and protected. The tree creates next year's growth before winter arrives, then waits. When spring comes, those leaves don't form. They simply expand. They unfurl from their compressed state, growing rapidly through cell expansion rather than cell division. This pre-formation allows trees to take immediate advantage of spring conditions. There's no delay, no need to build structures from scratch. The tree is prepared, carrying the future within itself through winter, ready to deploy it at the first sign of warmth. Trees can make soil on bare rock, nothing grows, but pioneer lichens colonize the stone, slowly breaking it down, creating tiny pockets of organic matter. Mosses follow. Eventually, a seed finds purchase. The tree's roots penetrate cracks, exerting pressure, secreting acids. Slowly, over years and decades, the rock fractures. The tree's roots delve deeper. When the tree dies, it decomposes, adding organic matter to the mineral fragments. Over generations, soil accumulates. What was bare stone becomes capable of supporting a forest. Trees don't just need soil. In partnership with other organisms, they create it. They transform the inorganic into the organic, the lifeless into the life-giving. Some trees have been worshipped as gods. Throughout human history, individual trees have been considered sacred. The Bodhi tree, under which Buddha achieved enlightenment. The oak of Dodona, where ancient Greeks heard prophetic whispers. The Yggdrasil of Norse mythology, the world tree connecting all realms. These weren't just symbols. They were specific trees, rooted in earth, living and growing. People made pilgrimages to them, left offerings, sought wisdom beneath their branches. Some of these sacred trees still live, though most are descendants of the originals. They're reminders that humans have always sensed something profound in trees, something worthy of reverence, ancient, patient, and enduring. Trees inspire awe across all cultures. A tree can be grafted to create multiple varieties. Through grafting, a single tree can produce multiple types of fruit. Orchardists can attach branches from different apple varieties to one trunk, creating a tree that produces several types of apples. The rootstock provides vigor and disease resistance. The grafted branches provide the desired fruit characteristics. They grow together, their tissues fusing, becoming functionally one tree despite being genetically distinct. This technique practiced for thousands of years, demonstrates trees' remarkable ability to accept foreign tissue. A tree can be a collaboration between different varieties, even different species, united in one form. Trees can live in extreme cold. In the Siberian taiga, Dahurian larches survive temperatures that drop to 60 °C or lower. These deciduous conifers shed their needles in winter, standing bare against snow and wind. Their wood is dense, their sap full of antifreeze compounds, their metabolism slowed to near dormancy. When short summer comes, they burst into growth, maximizing the brief warm period. These trees mark the northern limit of tree growth, the boundary between forest and tundra. They survive conditions that would kill most organisms, demonstrating that trees can adapt to nearly any environment Earth offers, short of the truly lifeless. Some trees drop branches to feed the soil eucalyptus, and some other trees regularly shed not just leaves, but entire branches. This self-pruning removes dead or dying wood and returns organic matter and nutrients to the soil beneath. The fallen branches decompose, feeding fungi, insects, and eventually the tree's own roots. It's nutrient cycling, the tree fertilizing itself, though the process takes years. This shedding also reduces the tree's water needs and fire fuel load. Less material to maintain, less to burn if fire comes. It's maintenance through loss, health through letting go. A tree's seeds can wait. Some seeds remain viable for decades or even centuries, buried in soil, waiting for the right conditions to germinate. Forest fires, logging, or storms that open the canopy trigger germination of seeds that have lain dormant for years. This seed bank strategy means a forest contains not just current trees, but the potential for future ones, hidden beneath the surface. The forest is layered not just vertically in canopy, understory, and floor, but temporally, with generations waiting their turn. Seeds are patience-made material, potential wrapped in protective coats, life deferred but not denied, waiting for its moment, which may come next year or in a century. Trees connect us to the past. Hold a piece of old wood, and you're touching something that was alive when your grandparents were young, or their grandparents, or even further back. Trees are bridges across time. A 500-year-old oak was a seedling when Columbus sailed. A 2,000-year-old sequoia was young when Rome was an empire. These trees have witnessed the entire span of recorded human history, standing silently as civilizations rose and fell, as borders shifted, as languages emerged and disappeared. They connect us to deep time, to a scale of existence we struggle to comprehend. In their rings, in their scars, in their persistent growth, they carry forward the memory of weather, of seasons, of centuries. They're living links to a past that's otherwise accessible only through books and artifacts. But trees were there. They remember in wood and root. Some trees can resprout from stumps for centuries. Coppicing, the practice of cutting trees to encourage new growth, reveals something remarkable. Some trees can be cut repeatedly, resprouting each time, with root systems that persist for over 1,000 years. In England, ancient coppiced woods contain stools, the stumps and roots, that date back to medieval times or earlier. The trunks you see are young, perhaps 20 or 30 years old, but the organism beneath, the root system, is ancient. These trees have been cut, regrown, cut again, in cycles spanning human generations. They've provided fuel, building materials, and tools for countless people while remaining alive. A partnership between human use and tree resilience that's sustained for longer than most nations have existed. A tree's leaves are designed to shed water. Look closely at leaves after rain. Many are shaped to encourage water to run off quickly. They have pointed tips called drip tips that direct water downward. They may have waxy coatings that repel water. This isn't just about staying dry. It's about preventing disease. Wet leaves are vulnerable to fungal infections. Standing water can block stomata, preventing gas exchange. So leaves are engineered to shed water efficiently. Watch rain falling through a forest. Water doesn't just drip randomly. It follows paths, channeled by leaf shape and arrangement, directed along branches and down the trunk to roots. Even the way water moves is shaped by tree architecture, by millions of years of evolution favoring forms that manage moisture effectively. And so, we've wandered through the forest together, discovering 50 more facts about trees, adding to the 50 that came before. 100 moments of wonder, 100 small insights into these silent giants that share our world. Perhaps you're still awake, mind gently turning over these ideas like leaves in your hand. Or perhaps you've already drifted away, carried into sleep by the rhythm of these words, by images of forests and roots and patient growth. Either way is perfectly fine. That's what this space is for. Trees have so much to teach us about patience, about resilience, about the value of connection and community, about how strength can be flexible, how age can mean continued growth rather than decline, how life can persist through damage and drought and fire. They teach us that we're not separate from nature but part of it, breathing the oxygen they release, walking on wood they created, living in a world they've shaped for hundreds of millions of years. Every breath you take connects you to trees, to the forests that cover our planet, to the ancient cycles that sustain all life. And they teach us, perhaps most importantly, about time, about how patience compounds into something magnificent, about how small, incremental growth, repeated endlessly, becomes enormous. A tree doesn't rush. It simply continues. Year after year, ring after ring, it grows. There's comfort in that, isn't there? In knowing that growth doesn't have to be dramatic to be real. That persistence, simple and steady, creates something lasting. That strength comes from deep roots and flexibility, from connection and community, from bending with storms rather than breaking. So as we come to the end of our time together tonight, take that with you, whether into sleep or into the day ahead. The patience of trees, their quiet strength, their generous way of existing, supporting others even as they grow, creating ecosystems from their own body, giving oxygen and shade and shelter and beauty. The forest is always there, in the parks near your home, in the wild places beyond cities, in the trees along streets, in the wooden objects around you. Every piece of wood was once alive, once growing, once part of a tree's patient accumulation of years. We're surrounded by trees, by their gifts, by their presence and their memory. And if tonight's gentle exploration through forests and facts has helped you find some peace, some rest, some small sense of wonder, then it's done what it meant to do. Consider liking, subscribing, sharing this with someone who might need it. Help this quiet corner of the internet reach others who are searching for calm, for knowledge delivered gently, for a moment's respite from the rush of the world. But whether you do that or not, know this: you're welcome here, always. Whenever you need to slow down, to breathe deeply, to remember that there are ancient, beautiful things in the world still growing, still reaching toward light, still standing patient and strong. Thank you for spending this time with the trees and with me. May you rest well, dream peacefully, and wake with a sense of the forest's quiet strength within you. Good night.